organometallic reagent, and let's use a Grignard reagent. So it looks like if we use this acyl chloride in the presence of an excess Grignard reagent, RMgBr, followed by acid on the last step, we actually introduce this R group 2 times. So we've gone from the acyl chloride to an alcohol that has 2 of those R groups. However, this one we're not going to look at the mechanism. If we use this organocuprate, this is that Gilman reagent again. Gilman reagent. This is a Grignard reagent. With the Gilman reagent, it looks like we actually only, say, substitute 1 time with this methyl group. So those we're only going to consider just at this extent, that if you take an acyl chloride with the Gilman reagent, it's going to add this methyl group here, say 1 time. What's very useful with chemistry is to take an acyl chloride and actually react it with an excess of Grignard reagent, and you actually have 2 substitutions. So why don't we take a look at a reaction like that? Let's take our acyl chloride and let's just make a ring, make it maybe a little easier to see. So we have this Grignard reagent in excess. We've seen this reaction a lot. We could have our Grignard reagents going to act as a nucleophile, attack the carbonyl carbon, form our tetrahedral intermediate, and we formed a new carbon-carbon bond, like this. Now, in this particular case, we have only 1 good leaving group. A really good leaving group with the chloride. It's going to take off. And so we have this species here. So now notice we've gone from an acyl chloride to a ketone. I should write it a little further down, maybe. So, to a ketone. And now we know that Grignard reagents will react with ketones. So let's have another equivalent. Let's put it together. Now this is fine. Another equivalent to the Grignard reagent. So original cyclohexane, let's have another one here. And we could put the counter ion in here as well. Now when we look at this reagent here, we do not have any good leaving groups. So we just have all of these carbons around. We've added our R group 2 times. So all we're going to do is wait till protein. Okay, so that would be our final product. So this is a very useful reaction. You don't have to just use this cyclohexyl Grignard reagent. However, any sort of wide variety of R groups, if you react an acyl chloride with an excess of the Grignard reagent, you'll end up having that being added twice. And it's just like with the hydride reaction. So here we go from the acyl chloride, in this case we're forming a ketone in the middle. We already know that the Grignard reaction works with these ketones, and so that's going to happen the second time. So that's nice that it connects back to our previous material. Okay. So then I think as I go down, yes, I have these numbered as these reactions. I'm going to scroll up just for a second here. And with these acyl chlorides, we've seen now a variety of reactions with different nucleophiles, but a lot of similarities in the reaction mechanism. So we've reacted with water to start with, or with an alcohol. We saw the parallel mechanisms that we can use to form a carboxylic acid up here in the top, or the ester that we have here in the middle. Instead of using those oxygen nucleophiles like water and alcohol, we could also have an oxygen nucleophile that's a carboxylic acid on the top here to form the anhydride. And here the slight twist is that we first deprotonated the carboxylic acid to make it a better nucleophile. And we use pyridine as a base for that. Rather than using these oxygen nucleophiles, we can do the same thing with nitrogen nucleophiles, such as ammonia. And you could use different substituted amines. So this could have R groups here rather than the hydrogens. We generate a variety of different amides that we have shown here. We just showed the simplest amide with ammonia. Similar mechanism and a little bit of acid-base chemistry kind of behind the scenes. And then we saw two other sorts of nucleophiles. Hydride, here for these reduction reactions. Similar idea of the mechanism. However, now the reaction happens 2 times. So hydride reacts with the acyl chloride, in this case to generate an aldehyde, and then reduces down to the primary alcohol. Some variations of the hydride reagents. And then finally, with organometallic reagents, very useful carbon-carbon bond forming reaction, especially with the Grignard reagent, is that we can add 2 R groups here, such as the cyclohexyl group, by taking a Grignard reagent and reacting with the acyl chloride. And this one we leave a bit as a mystery, but we can add just 1 R group using the less reactive Gilman reagent. So this will react with the very reactive acyl chloride, but it's not very reactive with the ketone that would be formed. So a lot of different reactions so far, but hopefully you can see the similarities of them. Okay, onward. So for these anhydrides, we want to think about how to make them and what to do with them. And this won't take long. There's not too much chemistry to cover here. Anhydrides, there's 2 ways commonly used to make them. Simple anhydrides like this, which is known as acetic anhydride up here on the top, can be made by taking acetic acid, 2 moles of it, and heating it up to a really high temperature. And what we're going to do is remove from the anhydride, and we're going to lose water. So if you were to balance this equation, you would see that we lose water. And again, that's why it's known as an anhydride. It's anhydrates. So we're removing water from 2 of these. This works for something like acetic anhydride because it can survive 800 degrees Celsius, but a lot of compounds will just decompose if you try to heat them up that high. However, we know another way now to make an anhydride. We saw that we can take an acyl chloride in the presence of pyridine and react this with something like acetic acid to get the anhydride. One thing you'll notice about the anhydrides here is that they have the same R group, a methyl group on each side here. It doesn't necessarily have to be the same group. You could have 2 different groups. However, a lot of times that can be difficult in preparing them or the reactions because you don't know, and this gets back to Crystal's question earlier, is here you have 2 potential leaving groups. And so if they're not the same, you can oftentimes end up with a kind of a mess in your reaction. So with the anhydrides, you will generally see those both being the same groups. And the most common one is this species here, which this is acetic anhydride. Not the most stable. It can react with water, as we'll see. What these anhydrides are really, in some ways, most useful for is introducing an acetyl or an acetyl group here. So we can take something like this compound, which is commonly known as salicylic acid, and react this with acetic anhydride and pyridine and introduce an acetyl group here, which then becomes acetylsalicylic acid, or this is actually the structure of aspirin. And so if you want to introduce this group here, using an anhydride is one of the most convenient ways to do it. Same thing for this particular compound here on the bottom left. Can introduce an acetyl group here to generate acetaminophen. So you can use this to make Tylenol. And it's actually quite interesting in a way that aspirin and Tylenol have such simple structures overall, but are so effective. And for these, let's see, I'm sorry, I'm going to go forward. Okay, I saved the space for the mechanism here. Why don't we do this for Tylenol? What happens turns out that the amine is a better nucleophile compared to the hydroxyl group. And so that's what's going to predominantly react. Let's have amine attack one of these two carbonyl groups. It doesn't matter which one. So now we're going to end up having our tetrahedral intermediate. O minus, let's just put this like this here, methyl group there. And now we have a good leaving group here because we can kick this whole group out. Let's see what that gives us. So this is all the same. We've reformed a carbonyl group. And then we've lost acetate, actually. And so this is a good leaving group, and that's why these anhydrides are quite reactive, because this negative charge is resonance and inductively delocalized. So that's why we have a good leaving group for the anhydrides. And then we have pyridine interaction, so let's use that in the last step here to deproteinate. So this is going to act as a base. And I'll just flip this around so it's in the regular zigzag. Now that we have pyridinium acetate. So very similar to what we saw with the acyl chlorides, is that now our leaving group for the anhydride on the left side of the mechanism is this whole species here, which is going to leave as acetate. And that's what's shown here on the right. So a good leaving group. All right, hopefully that's good. I will slowly scroll up here.